Section 36.4 Catalysis. A catalyst increases the forward and reverse reaction rates by the same factor. The catalyst remains intact after the reaction is complete or reaches equilibrium. A catalyst does not change the equilibrium constant. It changes the amount of time for the reaction to reach the equilibrium. Here is a typical mechanism for a catalyzed reaction from S to P. S denotes the reactant or substrate. C is the catalyst. Sc is the intermediate complex formed by S and C. And then P is the product. There are three elementary reactions. The first one is S plus C to form a complex. The complex may decompose back into S plus C. The complex can also produce P and release the catalyst. The catalyst can again react with a substrate. So I will talk about the enzyme catalysis because enzyme catalysis behaves exactly same as any other catalysts. The mechanism is the same. So we'll talk about this. 36.4.3 Michaelis-Menten enzyme catalysis. So enzymes are protein molecules that catalyze various chemical reactions. An enzyme increases the forward and reverse reaction rates by the same factor. Yet the enzyme remains intact after the reaction is complete or reaches chemical equilibrium. Enzymes do not change the equilibrium constant. So let's look at diagram here. We have the reactant or substrate here. We have the product over here. If we go from S to P, we need to overcome a reaction barrier. Over here, with the highest energy, this is the so-called transition state. By adding enzymes into this reaction system, it's possible for the substrate to bind with the enzyme and form this ES complex. The ES complex may overcome a smaller reaction barrier to form EP complex. The EP complex can overcome a really small energy barrier to form the product and release this enzyme, E. And that enzyme can again bind with a substrate to form ES complex, going over this lower barrier to form the product in the end. So this is the mechanism that consists of three elementary reactions. Again, this one S plus E to form the ES complex. The ES complex may decompose back into S plus E. It may also produce P. We have three reaction rate constants, K1, K minus 1, and K2. K2 is often referred to as the turnover number of the enzyme. This is the reaction rate. The reaction rate is dP over dt, of course. And P is involved in only one of the three elementary reactions. P is produced in this reaction. The rate is K2 times ES. So right here. Again, whenever we have multiple species and multiple elementary steps, it gets difficult to solve the Schrodinger equation. To solve the differential equation. So we're going to make steady state approximations to simplify the mathematics. Let's look at the ES complex. The ES complex is a intermediate. And usually this intermediate has a very low concentration. So what we do is this. We're going to assume the concentration of ES never changes throughout the reaction. Therefore, we have dES over dt is equal to 0. Well, this is actually a approximation. So I should change the equal sign to approximately equal sign. And then we have the expression for ES by looking at this algebraic equation. So ES is equal to K1 times S times E divided by K minus 1 plus K2. And this looks complicated, so we define a composite constant, this uppercase M, uppercase K sub M, as K minus 1 plus K2 divided by K1. So this way we simplify this equation. This M stands for Michaelis-Menten. Alright, so now we have ES is equal to S times E over this uppercase K sub M. Why uppercase K here? Well, it's almost like the equilibrium constant, right? For a reaction from ES to E plus S, right? So that's the reason. Alright, and then we have this equation. The reaction rate is dP over dt. It's K2 times ES. This is the reaction rate of the third elementary reaction. And ES is simply S times C over this uppercase K sub M. So right here. Now we're going to look at the concentration of S, the concentration of E. Of course, they keep changing. But we do know this, the sum of S, ES, and P is a constant because the substrate can exist in the reaction system in only these three different ways. Unreacted S, as in a complex, S is converted to P. So the sum of these three is a constant, and it's just S0. S0 is the initial concentration of the substrate. Again, we assume there's no ES or P in the reaction system at the beginning. Therefore, we have this equation. And then we can get the expression of the substrate, which is S0 minus ES minus P. So this is S. Now let's look at E. E is the enzyme. Enzyme can exist in two different forms: a free enzyme or enzyme in a complex. So E is E naught, the initial concentration of enzyme minus the complex. Now we have this equation over here. ES is equal to S times E over Km, being rewritten here by replacing S with S naught minus ES minus P, by replacing E with E0 minus ES. Well, why did we do this? Well, ES is a variable, it changes. S and E are also variables, they change with time. If you see an equation that contains three variables, usually it's very difficult to solve. So we are simply trying to reduce the number of variables. So right now, when we replace S and E, you can see we have how many variables? ES, that's a variable. ES is a variable. P is a variable, but now we have only two variables. Okay, and then we multiply both sides by Km, and we have Km ES is equal to this times this. We have only two variables. However, we prefer to solve the equation with only one variable. So we will get rid of the P. How can we justify the removal of P? P is the product. If we focus on the very early stage of the reaction, there's no P, right? As long as we measure the concentrations of all the species at the very early stage of the reaction, I think we can neglect the concentration of the product. Alright, so we're looking at subtraction. So over here, I'm going to assume this P is negligible compared to S0 minus ES. So basically, I just deleted the P. Alright, so again, if you're doing addition and subtraction of multiple items, well, if one item is much smaller than any other items, you can neglect that smallest item safely. Alright, okay, so now look at this equation. We have only one variable, that's just ES. We can solve this already, right? I'm just expand this. You have two terms multiplied by two terms, you get four terms. 1, 2, 3, 4, 4 terms. So we have a quadratic equation. Well, it's possible to solve it, but we can make it even simpler. Well, only because, again, in enzyme catalysis, it's observed that this ES, this intermediate complex, usually has a very low concentration, much lower than the concentration of S0. So what I'm going to do is I'm going to compare this term with this term. They have a common factor, which is ES, and then we'll compare the second ES in this term with the sum of S0 plus E0. And again, ES is much, much smaller than E0 plus S0. Usually we have this a very high concentration of S0 and very low concentration of ES. Remember, because of the very low concentration of ES, we used the steady state approximation. Alright, so we're going to make it even simpler. We're going to just assume this term, ES squared, is much smaller than this term. Alright. Again, why did we do that? We simplified a quadratic equation to a linear equation. So that's the only reason. Mathematically, it's easier. Now let's look at this. This is a linear equation. There's only one variable, ES. Alright, so we can solve it. We look at all items that contain ES, KM, E0, S0, we put them together and we have this nice equation. ES is thus equal to E0 times S0 over the sum of E0, S0, and KM. Alright, so that's it. Once we get the concentration of ES, remember the reaction rate is K2 times ES. We just replace ES with its expression. If you look at this expression, we can easily measure the initial concentrations of E0, S0, right? So I think this is, well, it still looks complex with so many terms, but again, E0 and S0 are the initial concentrations of the enzyme and the substrate. As a chemist, we usually measure the initial concentrations of the substrate and enzyme. So you are looking at many constants here. And we made an approximation early on. We assume that the reaction is at the very early stage. So it's better to put a 0 here or not, to remind yourself that we're talking about the reaction rate at the very early stage of the reaction, almost time 0. Almost time 0. Alright, so we have the reaction rate, it's this. And then we can actually measure the reaction rate or not, right? So how do we measure or not? Basically, we just, for example, we can measure the concentration of P at maybe 1 millisecond and then 2 milliseconds, and then take the difference, do a differentiation, we'll get the R naught. Alright, now we can further simplify this expression for R naught. How? Well, usually in enzyme catalysis, the concentration of enzyme is much lower than the concentration of substrate. Alright? This is very common for two reasons. First, we don't need a lot of enzymes. I mean, they are catalysts. They are not really consumed, so we just need a little bit enzyme to catalyze the reaction. Second reason is more practical or financial. I mean, enzymes are usually expensive. So that's why people use a very small amount of enzyme in experiments. And then because of this, we can just compare these two terms. Again, we're doing addition, so if E naught is much smaller than S naught, we neglect E naught. Just imagine this S naught is 1 million, E naught is 0.001. 1 million plus 0.001, what do you think? It's 1 million. Alright? So now we have this equation for R naught. However, there's a little problem here. If I ask you, how does this R naught depend on S naught? Well, it's difficult to answer. It's I don't know. Because you have S naught on top, you have S naught plus Km on the bottom, so S naught cannot simply cancel. So it's a little bit difficult to analyze this equation, so we're going to take the reciprocal of both sides. So 1 over R naught is equal to S naught plus Km over K2 times E naught times S naught. Why do we do that? Look, you have the sum on the bottom here, right? We cannot separate the sum in the denominator. However, if we flip the sum to top, we can separate them. So once we take the reciprocals of both sides, we can actually separate these two terms. One here and one here. Now it's really clear. 1 over R naught is linear with 1 over S naught, right? And if you plot 1 over R naught versus 1 over S naught, it's going to be linear with this slope and this intercept. You measure R naught, you measure S naught, you take the reciprocals, you make this 1 over R naught versus 1 over S naught. You look at the intercept and take the reciprocal of the intercept, and then you get K2 E naught. And then you look at the slope, and you know the slope is this uppercase K sub M over K2 E naught. This is how we determine this composite constant and K2 times E naught experimentally. Well, I prefer to call this Michaelis-Menten composite constant. Okay, so what if we use a lot substrate? Well, in that case, this 1 over S naught approaches 0. So again, if you use, a huge amount of S naught, you're going to see this term is negligible. And we have 1 over R naught approaching 1 over K2 E naught. In that case, we have R naught approaching K2 E naught when S naught approaches infinity. So really, you just need to use a huge amount of S naught and measure the initial reaction rate. It's K2 times E naught. Sometimes if you don't want to use a huge amount of S0, you can do some extrapolation carefully. Okay, now we have this equation here. We just define R sub max to be K2 E0. R sub max is the maximum reaction rate when you use a huge amount of the substrate. The reason we define this R max is, again, to simplify this equation. Now 1 over R naught is simply this. The intercept is 1 over R max. The slope is Km over R max. Alright, and again, we can just make this 1 over R naught versus 1 over S naught plot. Sorry about this. This should be a regular font. By the way, 1 over R naught should be the vertical axis. 1 over S naught should be the horizontal axis. You make this plot, it's called a Lineweaver-Burke plot. And again, the slope is Km over R max. The intercept is 1 over R max. If you divide the slope by the intercept, you get this Michaelis-Menten composite constant. If we also know E0, it's not too difficult. Again, as a chemist, you are supposed to measure the initial concentration of the enzyme. And then you know Rmax, you can calculate K2 easily.